Today we're starting Unit 4, which is going to be on exponential and logarithmic functions. Today specifically we'll be looking at the exponential function and its inverse. You looked at the exponential function for the first time in grade 11 math. You saw it's useful to describe relationships where something's growing quickly or possibly decaying. Usually we look at bacteria growth or compound interest problems. And we'll also, in this unit, be looking at how we can use graphing technology to explore the nature of both the exponential function and the inverse of an exponential function. So from grade 11, the exponential function has the form y equals a times b to the power of x, where a is just a constant such that a cannot equal 0. B is a base, where b has to be greater than 0, and b cannot equal 1, the base can't be 1. As well, a and b are elements of the real numbers. So some examples of exponential functions: we could have a function like 3 times 2 to the power of x, or a function like 0.7 times 5 to the power of x, or even a function like negative 2 times pi to the power of x. Okay, these are all examples of exponential functions. So we want to just quickly examine the exponential function y equals 2 to the power of x. And we'll be looking at average rate of change with respect to this function. So what I'd like you to do is complete a table of values for this function. And you can see I've started my table of values here. So I'm going up. So you can see I've started my table of values here. I'm going up to x equals 6 from 0. And filling in my numbers as I go, my answers as I go. And once I've done that, I'm going to start calculating my first, second, and third differences. And I want to see if there's a pattern to these differences. You can fill in the first differences and the second differences too. Compare answers to me. So there's my first differences. And my second differences. And my third differences. And always looking for patterns, I'm definitely seeing a pattern in these differences. Okay, my numbers from my y values are just being repeated. If we think back to polynomial equations and polynomial functions, when we calculated differences, we were looking for a constant difference, and that was the difference that corresponded to the degree of our function. I can tell by looking at this that if I kept calculating differences, I would never find a constant difference. But the bigger question is there a pattern to these differences? Is there a way we can tell just by looking from a table of values what type of function we're looking at? Just to reiterate, in linear equations, the first difference is constant. In polynomial equations, the nth difference is constant, where n is the exponent of where n is the highest exponent. And in exponential equations, successive differences are proportional. So let's just take a look at what that looks like, what that means. In exponential equations, successive differences are proportional. So if I look at a pair of differences and I divide one by the other, get a value. Here my value is 2. If I look at other successive differences, and I divide one by the other, I also get a value of 2. And if I do that to any of these successive differences, we will always get this constant value of 2, our proportional value. And that's how we can tell by looking at a table of values if we're dealing with an exponential function. Okay, another example just around exponential functions. We would like to write an equation to fit the data in this table of values. So the general form of our exponential equation is y equals a times b to the power of x. We can pick some values from our table of values to sub into the general form of our exponential equation. For example, when x is 0, y has to equal 1. Anything raised to the power of 0 becomes 1. So this tells me that my a value, my constant, is 1. My second number that I can pick, I'll pick an x value of 1. So my y value is 4 when my x value is 1. Anything raised to the power of 1 is itself. So this is telling me my base is 4. So based on this table of values, my exponential equation is y equals 4 to the power of x. One last thing I'd like to do, a little investigation, and you can follow along. What does the graph of the inverse of an exponential function look like? So if my function is y equals 2 to the power of x, I'd like to graph this function, I'd like to graph the inverse, and then graph the line y equals x. So I'm going to create a small table of values. So making my table of values from -3 up to +4, I end up with this. I can graph this function. So just quickly plotting my points. I have a point at 0 and +1. I have a point at 1 and +2, 2 and 4, 3 and 8, and then I'm off my scale way up here. In the negative side of things, I have a point at -1 and 1/2, -2 and 1/4, -3 and 1/8. Really hard to draw that based on my scale, but our exponential curve will look something like that. If you think back to grade 11 math, when we found the inverse of a function, and here we're finding the inverse of the exponential function, we would do that by swapping the x and the y values. So here we're finding the inverse, and we're doing that by swapping the x and the y values. So if I plot that, when x is 1, my y value is 0. When x is 2, my y value is 1. When x is 4, my y value is 2. When x is 8, my y value is 3. When x is 16, off my scale, my y value is 4. And going back the other way, when x is 1/2, my y value is -1, and so on, and so on. So I'm trying to make this a nice smooth curve. My inverse exponential function looks something like that. If I graph the line y equals x, we can see that the exponential function and its inverse is just a reflection over that line. xx. The last part of the question asks us to state the domain and range of these functions. For the exponential function, the domain is x is an element of the real numbers, and then there's no restrictions on the x values. The range, y is an element of the real numbers, such that the y values are greater than 0. So there's a horizontal asymptote at the x-axis. For the inverse function, we're swapping the domain and the range. So for the inverse function, our domain is x is an element of the real numbers such that x has to be greater than 0. So here we have a vertical asymptote, and our range, which has no restrictions. Y is just an element of the real numbers. So that's a little refresher on the exponential function and a little introduction to the inverse of the exponential function. In tomorrow's video, we'll be going a little bit further into the inverse of the exponential function. We'll define it a little bit more. Thanks for watching.